Yes. So on homework 12, it had this is a simple, it had our x, y, z. So it had the x, y, z is equal to 1, 2, 3 plus t 1, 4, negative 6. And it was just asking for perpendicular, and we wanted to know if there's any way better to find the perpendicular for a 3D vector than just kind of guess and check.
You know, what happens in 3D is you have so many possibilities that I think it's easier just to guess and check. Because all you want, you're trying to create something that's got a direction vector whose dot product with this is 0. But remember, in space, in 3 dimensions, if this is our line, there are a whole bunch of lines that are going to be perpendicular to that. So, I mean, it's not like it's searching for a needle in the haystack kind of thing.
Yeah.
So that's what I would do. It's just, you know, you can actually pick whatever you want for the first 2 values. And then if you need to, you can solve for the third one. That makes sense?
Yes.
Okay. What else?
So on number 41 on homework 12, it gave us a sphere with the equation x minus 1 squared plus y minus 2 squared plus z minus 3 squared equals 25. And it wanted us to look for the circle, and we found the center, which is just x minus 1 squared plus y minus 2 squared.
So the center is going to be 1, 2, 3. So we got this sphere.
It's looking for a circle.
Just any circle or one that goes through a particular point?
Describe the set of points of S in the xy plane that are also on the sphere whose equation is this. So it's a circle on the xy plane.
Okay, so your circle was x minus 1 squared plus y minus 2 squared.
Yeah.
And then did it give us, it must be equal to 25.
No, in the answers, it had it as is equal to 16. And we had no idea what the radius was 4 instead of 5.
Well, so what's happening is that, you know, this is going to be kind of hard to visualize. So we have this circle, or sphere rather, so we're thinking 3 dimensions. You know, its center is right here at 1, 2, 3. And so its radius is 5, so that's 5. But if we take a circle, so this now is up, since its y is 3, it's up, it's sitting, you know, if we do our xy plane like we think of normally, you know, here's our x and here's our y. And this is going to be centered at 1, 2. So we're going to have our circle doing something like that. So this sphere is sitting, like if we're looking down, it's like pulled up 3 from there. So where this is actually intersecting is going to be somewhere down in there. So it's not, you know, this has center at z coordinate 3. We're down here at z coordinate 0. And so at that part of the circle, our radius isn't going to be as big as it is here, you know, like at the equator. Does that kind of make sense?
Is there any way we would know what the radius would be, or is that just kind of
Well, they're giving us this, right?
No, they didn't.
Oh, well, what are they giving us then?
They just gave us the equation of the sphere.
And they want us to find the circle in the xy plane. I think we can do this. Do they say to find it, or do they just tell us that?
Describe the set of points of S in the xy plane that are also on the sphere whose equation is x minus 1 squared plus y minus 2 squared plus c minus 3 squared is equal to 25. Give an equation of S.
I think we can do this. So we don't know this yet, right?
No.
This is what we're trying to find. So let's do this. Now we know that whatever we picked for R here is going to make all the points on this circle also be points on this sphere. So all of the values of x and y that make this a true statement have to also make that a true statement. So let's solve this system. Now we also know that because we're in the xy plane, we also know what is z equal to? 0. So that combination of things, we can sub these into there. And then I think we're going to be able to solve and find out what the radius is. So we can say, this part right here, the x minus 1 squared plus y minus 2 squared is r squared. So I'm going to replace that by r squared. We know that the z is 0. So that's going to be 0 minus 3 squared is 9.
Yeah, there it is.
Yeah.
So that's the r squared is 16.
Yeah, that makes sense now.
That's weird to visualize, isn't it?
Yeah.
Crazy.
And what else that we wanted to talk about was the, like, 2I minus j plus k stuff.
Okay, and do you remember which one that is? Or what?
Yes, that's homework 13, number 5. What page is that? That was a large page. It gave us u is equal to 2I minus j plus k, and v is equal to I minus k.
I minus k?
I minus k.
So I, j, and k are known as the unit vectors in the direction of the x-axis, y-axis, and z-axis. So I is that unit vector in the x direction. So if you imagine, here's our, we said this is x, that's z, and that's y. So this is I. And j is the unit vector in the direction of the y-axis. So it's going to be, that vector there. And z, or k, is the unit vector in the z direction. So it's going to be that vector there. So it's just an alternative way of writing these. So when we say u is 2I minus j plus k, that's the same thing as saying 2 comma negative.
Okay, that makes more sense.
And then this, because it doesn't have the j, is going to be 1 comma 0 comma negative 1.
Okay.
That
Yeah,
makes
so it's just notation there. But it has some certain uses, and we'll be coming back to this
Okay.
some more. Does that resolve things?
Yeah,
then?
that was all,
Yeah.
that makes sense
Okay.
a lot.
Anything else?
Oh, 67. Oh, it's a Larson page. It's the one that's 48,000. Yeah, it's a 48,000 pound truck on a hill of Davidtown.
On a hill,
On a hill that has
a slope,
oh, hill has a slope of 10 degrees.
10 degrees. This is exactly the example we were going to do to start with, so this is a great place to start. And we want to know what's the force we need to keep it from rolling down the hill. So the brakes fail, it's going to roll down the hill. So the idea behind this, we're going to try to kind of use our projection, vector projection comes into play. So our truck is, sitting here on this hill. Trucks. So our truck is sitting there. Now, what we mean by the 48,000 pounds, that's actually a force. And a weight is a force, and it's all acting down. So this is a vector that's going down. So we can write that as that, shall we say, weight vector. Now it's all going down. It's 48,000 pounds, and down is negative. None of it's going horizontally. So that's going to be 0, negative 48,000. That's that weight vector there. Now, what we want to know is how much of it is actually going down the hill. Right? That's our question. Because if we're going to try to stop this truck from killing somebody, we don't really have to have 48,000 pounds of force to stop it from going down at that angle. Because some of that is not going to be going in that angle at all, right? So we just have to figure out, what is the magnitude of that purple vector there, which we're going to, I made it too big. imagine we're drawing that perpendicular to, so we're looking at that projection of the weight vector onto that purple vector of the slope of the hill. And so then once we can get what that, and actually we just want the magnitude of that. So I'm going to call that purple vector, I'm just going to call it a force vector. Okay, so the purple vector now is what we're trying to find. Okay, so we are going to get that projection of W onto F, what we need is to get the magnitude. So the magnitude of F is going to be the magnitude of our projection of W onto F. Does that make sense? And we said from what we talked about last time, it's going to be, do you remember what that is?
Is it U dotted with V over the magnitude of V squared times B?
Oh, well, that's for the whole vector. So and we don't really need the vector. So the vector itself, so the projection of U onto V is U dotted with V over the magnitude of V squared times the vector V. But remember, we separated that out and said we could think of that as the magnitude of U dot V over the magnitude of V times a unit vector in the direction of V. Is that okay? And this part right here, because this is a unit vector, that's a vector of length 1, this is that magnitude of the projection vector. So our magnitude of the projection of U onto V is going to be just the U dotted with V over the magnitude of V. Is that okay? Okay, so we know our U vector for us is this weight vector right here. Now what we need is a vector that we're projecting onto. And it would be even slicker if we could pick that vector to be a unit vector, because then this would be dividing by 1. The magnitude of a unit vector is 1. And we would just take U dot V, and that would be our magnitude. How much of that weight is going down the hill at that 10-degree angle. Does that make sense? Mm-hmm. So let's call this, I'm going to look at, first I'll look at, well, we can do it right here, I think. So let's see what a vector here, yeah. So if I want to know what this vector is, this vector V I'm going to call right there. That's that white vector. I'm going to make it a unit vector because it's going to be easy to make it a unit vector. So here's a triangle, and that's 10 degrees. That must be, and that's perpendicular here, and that must be,
No, 80.
and then minus 10.
Oh, yeah.
Okay, 80. So that's going to be an 80-degree angle there. There's going to be some hard arithmetic in here. So a vector in that direction, we can say that the components of this vector are going to be, I don't want to say, I'm trying to pause and try to explain what I'm doing here. So let me redraw a vector here to make this even easier, I think. Let me make the right angle right here. Now, there, 10 and this angle are now alternating interior angles. Mm-hmm. So now this is a 10-degree angle. This is even better. And this is our vector V here. And we're thinking unit vector, so we're going to make this have a magnitude of 1. That means this hypotenuse is just 1. So what's this horizontal component there going to be? This is the adjacent. This is the hypotenuse. Cosine of 10 is going to be x over 1. X is going to be just cosine 10. And what about the y?
Y
Why is just a sine?
sine of 10. And remember, because we know our favorite trig identity, sine squared plus cosine squared equals 1, no matter what the angle is, we know that's got a magnitude of 1. So there's a unit vector, and it's pointing in the direction that we want. Maybe it should be negatives, but it won't really matter. Is that okay? So we're going to then, what do we have to do? So we're going to take our vector W, we're going to dot it with our unit vector, cosine 10 degrees, sine 10 degrees. And we're going to divide it by the magnitude of our unit vector. But we know that's just sine squared 10 plus cosine squared, that's just 1. Is that okay? So our W vector, all of it was going down. So that's 0, comma, the negative 48,000. We're going to dot that with our cosine 10, sine 10.
Negative 48,000 sine.
Yeah, and remember now, really what we want, you know, it's a magnitude. Well, I mean, if we do this, we're going to get a negative number. But we want really we're talking about the magnitude. That force is coming down this way. But the magnitude is going to be just an absolute value. So it'll just be whatever 48,000 times sine of 10 is. Did you get that? Is that the answer? What was it?
8,335.113.
103. And this is pound, force is not measured in pounds. So the idea is, you know, even though the truck weighs 48,000 pounds, that's going down. Since we got even that little bit of a slope is going to mean that we don't really need the whole 48,000 pounds to push up against that. We're only going to need a little over 8,300 pounds. You know, so probably you and who you're lifting with, Colin, could get out here and just hold it. Because you don't ever go light, right? So if you both are there doing that, we'll be fine. Call the repairman. Call the guy to come fix it. Get the tow truck. All right. Anything else?
That was it.
That's perfect. That was exactly the kind of example I was going to start with. But we did that. So I can jump on. Continue on. So we're going to talk about work. Let's do some work. So we have talked a little bit about this before, but work, so work is sometimes defined as mass times distance. And this is if F is a constant force. So if F is a constant force, whose direction is the same as vector AB, which is our displacement vector. Vector, yeah, how much we're going to move it. So the idea is that if we have some object and we're trying to move that object, let's say, I can call A right there, I guess. We're going to move that object. Doesn't change shape. There. So we're going to move it there. So we're going to slide that box over there. And that box weighs whatever its mass is.
Mr. Street, what does that say? It says whose direction is
The same. Same as the displacement vector. Now for us, we're going to think of this mass, we're going to be talking about a weight. So we're going to think of that as being a force. And so we will make this into work is going to be the magnitude of that force, that weight there, and then times that's displacement, which is going to be this distance here, which is going to be the distance from A to B. That's the displacement vector. Now that's in the simplest case where, this is our truck standing on level ground. Colton is here. Maybe he's got his friend, and they're all pushing in that same direction, which doesn't always happen, okay? So now we're going to say so that's where the force is in the direction that we're trying to move it. So the force, that we're pushing here is in the same direction that we're trying to move that object. But we know that that's not always the case. So if F is a constant force, in any direction, not necessarily the direction we're trying to push that thing, then the work done I'm going to call work capital W, work W done by that force F in moving the object from A to B my claim is, we're going to try to convince you that the way we can do this is going to be W is equal to the force vector dotted with the vector AB. So, let's imagine there's our object. We move it. I'm going to do it this way. But really, if this is A, then the B is way over here. We don't want to take away the width of that object. And our force is acting maybe not in the same direction, but our force is somewhere around here. So to get that same idea that we talked about, we want to know, when we had the force being applied in the same direction, then we said that the magnitude, that the work was the magnitude of that force times the distance AB. So what we want now is, the equivalent of that is how much of that force is going in that direction. So that's what we want, the magnitude of that force that's going in that same direction that we're moving it, times that distance AB. Well, this, we've talked about, that's the projection of our vector onto the vector AB. And so what we want is for this to be the magnitude of our projection of the force vector onto AB. That's going to be, so we said before the work was mass times distance. Let me go back up here. It was mass times the distance. And we're going to talk about that mass as being the magnitude of the force. This is where we're going in the same direction. And the distance is going to be the magnitude of that vector, we're moving it from point A to point B. Let me slow down a minute and make sure we're understanding that. So this is going to be how much, that weight of that thing there, that force that we're going to move over times that distance. But this weight is going to be the magnitude of that force. So that's how much of this are we going to have to push this way is going to be our magnitude of the projection vector. And then the distance that we move it is going to be our magnitude of AB. That's going to be from point A to point B. What is that length? What is it? The length of that vector that we're moving it. Is that okay? Okay. So we know then that the way we get that projection, the absolute value of the projection vector, well, we know that's going to be, how do we get that again? That's going to be,
Do we want to use F and AB?
we use those same,
So F dotted with
F dotted with AB, that's our U dot V, over magnitude of AB, that's our magnitude V. So that's that part there. And then we're taking that times the magnitude of AB, and then we cancel. And so remarkably, the work done is going to be the dot product of the force vector with that displacement vector, which is clean and simple. That's nice. We like simple. So let's see how it works. So if we have, find the work done. Find the work done by a 10-pound force, in the direction of the vector 1, 2 in moving an object three feet from point 0, 0 to the point 3, 0. It's all good in theory, so what do we need? We need a force vector, and we need a displacement vector. Should we tackle the force vector? So our force vector is 10 pounds of force. What's that 10 represent? What is it? R. Remember, we need, in vectors we talk about, magnitude and direction.
So that's the magnitude.
It's the magnitude, so that's how big the force is. So we know that our magnitude of that force is 10. And its direction is 1, 2. Okay, so now what we want to do is write F as a vector with magnitude 10 pointed in this direction. Can I just say 10 times this vector? No. Because if I did, it'd be 10, 20. And the magnitude of 10, 20 isn't going to be 10. Problem is this is not length 1. If this was a unit vector, then I could multiply it by whatever I wanted and create a vector with that magnitude. Does that make sense?
Mm-hmm.
So what I want to do is make this into a unit vector that's pointing in this same direction. And then I can multiply that by 10 to make it be in this direction with magnitude 10. With me?
Mm-hmm.
How do I make that into a unit vector? That's a good answer. What is its magnitude? So I'm going to call this vector right now, I'm going to call it D for the displacement vector, I'll call it direction. It's the direction we're moving our force. Okay, what is the magnitude of D? Square root of 5. Right, so that's bigger than 1. Okay? Square root of 1 is 1, square root of 5 is bigger than that. So this is not a unit vector. To make it into a unit vector, we're going to take D and divide it by its magnitude. That's called normalizing it when you divide it by its magnitude. So you can take any vector you want, divide it by its magnitude, and you create a unit vector, a vector of length 1. So when we do that, we're going to get our vector D divided by its magnitude is going to be that 1 over square root of 5, comma, 2 over square root of 5. I'm still pointing in the same direction that we want. But the good thing now is it's got a magnitude of 1. Its length is 1. So we want our force vector to be in this direction, but have that magnitude. Now we can multiply that by 10. So our force vector is going to be 10 over square root of 5, comma, 20 over square root of 5, but we really shouldn't leave it like that. You're okay with that? We can rationalize that.
That's just going to be
Which was good. This can be 10 square root of 5 over 5, 20 square root of 5 over 5, and now we got to do better than that. 2 square root of 5. See, once you start, it never ends, right? So there is our force vector. Okay? It has magnitude 10, and it's in the direction of the vector 1, 2. So we, just a picture that's kind of lurking behind the scenes. And, we do this all the time, especially if the thing we're trying to move is down low, right? So we're trying to move this thing over from 0, 0 to 3, 0. We're trying to move that object over. But it's down low. We don't want to, get down there and push it at ground level. So we're going to, push it at 1, 2, and we're going to reach up there and we're going to pull it like this. We're going to pull it like this. So we're going to reach down and we're going to pull that thing to move it this way. And so in that way, we're moving it here. So how much work are we really doing? Well, the work we're doing is going to be the force vector dot with, well, what's our vector AB? Yeah. From 0, 0 to 3, 0 is tip minus tail. It's going to be 3, 0. So we're going to get our, what do we call it, 2 square root of 5, comma, 4 square root of 5. We're going to dot that with the vector 3, 0. So the work that we actually end up doing, 6 square root of 5, and I think when I did that, what did I get as a decimal? Like 13.416. What's the units going to be on that?
pounds.
So work is a weird thing because, this is in pounds and that is in feet. So it's foot pounds is what they call it. It's not per because, it's not a division. It's a feet times pounds. They call it foot pounds. It's a work unit. Forces in pounds. We're moving at a distance. The work we do is going to be in foot pounds. Okay, now we're going to change gears, and we're going to look now. Let's do some 3D work again here. So we know that in 2D, that we talk about, a vector, and it has a magnitude, and we talk about that angle it forms with positive x-axis. So in 3D, life is never that simple. So we imagine where x comes out, z goes up, and y goes across. So if we look at some particular vector, now I'm going to try to show this. So if we come, out and over and up to this point here, then this is our vector V. And then use your imagination there. So we're out from the chalkboard to the right a little bit and up a little bit. Now, instead of talking about an angle, we talk about the angle that this makes with the x-axis, alpha, and the angle that it makes with the y-axis, call that beta, and the angle that it makes with the z-axis, which we'll call gamma. So in our quest to make you fluent, that's going to be a gamma. Okay? So we call these, alpha, beta, gamma are the direction angles. And then we sometimes also talk about cosine of alpha, cosine of beta, and cosine of gamma as the direction cosines. So we're going to see if we can find those. Turns out it works out pretty slick. Okay, so far. So we're going to use again now this idea of, I is that vector 1, 0, 0. It's a unit vector in the direction of the x-axis. J is that vector 0, 1, 0. It's the unit vector in the direction of the y-axis. And K is going to be 0, 0, 1. It's going to be that unit vector in the direction of the z-axis. So we know that the cosine of alpha, the cosine of that angle alpha, is going to be what we know as u dot v over magnitude u magnitude v. So for us, we're going to take this vector v dotted with, let's pick that unit vector in the direction of the x-axis that we're calling I. Is that okay? So that's going to be v dot I over magnitude v magnitude I. You with me? Now let's say that v is going to be v1, v2, v3. There's the components of our vector v. So this cosine of alpha, when we take v dotted with I, we're taking this v1, v2, v3 and dotting that with 1, 0, 0. You just get v1. Is that okay? I'm going to leave magnitude v as magnitude v. What is the magnitude of I? It's a unit vector. It's just 1. So we get v1 over v is the cosine of alpha. Oh, that's nice. Any predictions on the cosine of beta? Yeah, because you're gonna take v dotted with j, and when you dot it with j, you're gonna pick off that y component of vector v, so you get v2, and you're still gonna have magnitude of v times the magnitude of j, but j is also a unit vector, so we're there. And the cosine of gamma is v3 over magnitude of v. Oh my gosh. Now we say that we call let's say that it's going to be so a unit vector in the direction of v, a unit vector in the direction of v. Remember how we do that? So you take v divided by its magnitude. And this is called the normalized vector. So when you make it into a unit vector, it's called the normalized vector of v. So when you normalize vector v, you just take V divided by itself, or V divided by its magnitude. Well, that's going to look like, what's that going to look like? So V divided by its magnitude is going to be V is V1, V2, V3. We're going to divide through by the magnitude. That's going to divide each of those by the magnitude.
V1
Don't just comma. This is still a vector. V2 over magnitude V, comma, V3 over magnitude V. What we just said,
So that's just the cosine.
cosine of alpha, comma, cosine of beta, cosine of beta. Isn't that crazy? And because that's a unit vector, right? It's a unit vector. That tells us what must be true about cosine squared alpha plus cosine squared beta plus cosine squared gamma.
Does that need to equal to each other?
It has to equal 1. Okay? Okay?
Yeah.
So we know that cosine squared alpha is cosine squared beta is cosine squared gamma. That's because that's a unit vector.
Yes, I know.
Okay, let's do an example. So V is going to be 2I plus 3J plus 4K. Can we, first of all, find the direction cosines? And then can we find the direction angles? Then can we show that cosine squared alpha plus cosine squared beta plus cosine squared gamma does indeed equal 1? Okay, throwing a lot at you fast. Can we sort it out? So here's our V. Should we write V like we're a little more familiar? What's that going to be in component form?
2, 3, 4.
2, 3, 4. And how do we start the ball rolling here? Yeah, we got to find the magnitude. We're going to divide V by the magnitude. So first let's find what is the magnitude.
25, 29.
Good. So it's 2 squared plus 3 squared plus 4 squared. So that's 4 plus 9 plus 16. So 16 and 4 is 20. So not very pretty, but it's square root of 29. There's our magnitude. So then you said we're going to normalize V, or find a unit vector in the direction of V. So we're going to take our vector V and divide it by its magnitude. So we're going to divide each of its components by the magnitude. And that's going to look like
2 squared, 29, 3 squared, 29, 4 squared.
yes,
4 over squared.
magnitude. Okay, so now that's supposed to be helpful, and I'm about to destroy the evidence. So I hope you took good notes. So part A, the direction cosines are going to be that the cosine of alpha is,
Just over square root.
that's that x component, and the cosine of beta,
3 over square root.
and the cosine of gamma.
4 squared.
There you go. Kind of cool. Then part B, we got to find the actual angles. This is where you bust out your calculator, taking great advantage of that inverse cosine feature. Let's round it to the nearest tenth of a degree.
is the nearest 10th, correct?
10th of a degree, yep. Did you get, anybody get alpha?
68.2.
Nice, 68.2 degrees. And let me know when you got beta.
56.1.
Pretty good. And gamma.
42.0.
Nice. The agreement? So, I mean, it's a little hard to visualize, but you can see where that's going to pin it down in terms of location. You know, you've got your X, Y, and Z, and you're going 68 degrees from the alpha, and that's from the x-axis, and 56 degrees from the y, and 42 degrees from the z. And then I guess that's helpful. It's hard to visualize, I think. All right, and how are we going to show that that's true? So we're going to take our cosine of alpha squared plus the cosine of beta squared plus the cosine of, oops, it's gamma squared. So that's just going to be 4/29 plus 9/29, 16/29, 29/29, and we got 1. Crazy, crazy, crazy. How about that? We did it. Wasn't sure we could pull that off. Should we do another work one? Got a couple of minutes? So pull with a constant force of 50 pounds at an angle of 60 degrees. Find the work done in moving an object 12 feet.
Magnitude. Yes, we know that's 50. So if we want, we need an angle. A unit vector in that angle, right? So
What's the angle?
60.
So always the horizontal is going to be cosine of that
Cosine
angle.
60 and sinus.
Yeah. So you can always create a unit vector in that direction by going cosine of that angle, sine of that angle.
Oh yeah, because that.
You know it's a vector of length 1 because sine squared plus cosine squared of any angle is 1.
Not work, because when you square that, it's cosine squared of 60 plus sine squared of 60, and that's just cosine squared plus sine squared. I'm not squaring it yet though.
Yeah, I think he's just writing the vector. So you're saying cosine 60 is a half, is that right? And sine of 60 is square root of 3/2. So he's just writing the exact values of that. What was our vector AB real quick?
Isn't it just 12 0?
Oh, yeah, and then you want to just dot those.
So no, that one's 300. The work comes in.
Quit trying to be easier.
More.